let's consider a problem that we can use some constant acceleration principles to solve. Here we have a dragster that can achieve an average acceleration of 26 meters per second squared. Well, that doesn't say constant, but it does say average. So what we can do is we can say, because for constant acceleration, the average acceleration is equal to instantaneous, I can use, anytime I have an average acceleration, I can use constant acceleration equations to analyze that situation, just knowing that, okay, that's assuming that the average is that constant acceleration through that region. So that's what we're doing here. As we read the statement, it's useful to make a little diagram and write down the things we know and the things we don't know. So we can achieve an average acceleration. Here's, we've got a dragster. We've got an average acceleration that we'll just call, my acceleration is 26 meters per second squared. We've got some axes that we write down for our diagram saying, okay, x is positive to the right, and so we're accelerating to the right. Lovely. Suppose we accelerate from rest at this rate for 5.56 seconds. So we'll say my final time is 5.56 seconds. How far does it travel? Well, we'll say I can say the initial position. I just choose, based on my coordinates, where I want this initial position to be. So I'll say my initial position is 0. And then my initial velocity, it says from rest. Anytime we see from rest, we can say my initial velocity is 0. Or if it ends up at rest, then your final velocity is 0, right? But initial velocity is 0 because we start from rest. And now what do we want to find? We want to find how far it travels. So we want to find final position. We can now look through our constant acceleration equations. We want to find something that can have as many of these things that we know. So x naught, v naught, a, and t are all fine. Ideally, it wouldn't have things that we don't know aside from the one thing we're trying to find. If we can't get a single equation, we can write multiple equations and solve simultaneous equations. But here it looks like, if I look at those constant acceleration equations, there's one here that does exactly what I want. It says that my final position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. And I know all of these things on the right, so I can just plug them in and solve. Let's do that. Initial position, 0. Initial velocity is 0, so those terms go away. And then 1/2 at squared, we can plug stuff in for that. So x is equal to 1/2 at squared. That's 1/2 26 meters per second squared is the acceleration, and 5.56 seconds is how long that's happening for. You evaluate that, and we end up with 402 meters as the final position. So how far does it travel? In 5.56 seconds, it travels 402 meters. How about the final velocity? Well, now we've got a different thing we're trying to find. So for this part B, or this problem 3.9, we can now say, what do I know? Well, now I know final position as well, in addition to initial position, initial velocity, acceleration, and time. So I know all those things. What I'm trying to find my final velocity, v. So I look through my constant acceleration equations, and I try and find one that can have any of the things I know, and hopefully only one thing I don't know, just to make my life easy. And I find it, it's one that looks like this. My velocity squared is equal to my initial velocity squared plus twice the acceleration times final position minus initial position. We can plug in the things we know, and note that my initial velocity is 0 and my initial position is 0, so those terms go away. And we end up with v squared is equal to 2ax. We can take the square root of both sides and say then that v is equal to the square root of 2ax. Plugging in the things that we know, square root of 226 meters per second squared, if I can write it, times my final position now, I know from the previous part, 402 meters. And when evaluated, we get 145 meters per second. It's pretty darn fast. That's assuming that we keep accelerating at that rate throughout. That gives us a final velocity of 145 meters per second at the end of that time interval.